Now, the next part here we are going to start with today is allocation methods. In the main memory chapter also, we discussed about contiguous allocation. Now, something similar is also available in this very part of the chapter. First type of allocation is contiguous allocation. So what does it mean is whenever a file is allocated some space, whether it is allocated contiguous allocation or it is distributed over the secondary storage, that is what we are going to discuss. Now, why I'm discussing this, because this is very important part of the chapter where we will be actually looking at and comparing certain methods. So each allocation method will have its own advantage, like contiguous allocation, as the name represents. So we will be having a starting location, which is called a start block number, and we will have a length of that or the number of blocks those are allocated for a particular file. So if there are n blocks, those are needed for a file, and it starts with the location B, then it will occupy blocks like B, B1 plus 1, B1 plus 2, and so on till Bn minus 1. So in the memory, all these blocks are basically contiguous. So that is what is being represented by contiguous allocation. Now, the there are distinctive features of these allocations. One is it is easy for implementation for sure. And the other one is that it provides us the sequential access. So whenever we have to read the file, so it will act sequentially. So we start from block B and keep reading all the blocks till B plus n minus 1 to read the whole file. Also, this approach provides us with direct access. Now, these are two very distinctive features of this allocation method. One is a sequential access and another is direct access. So let us suppose we wanted to access a particular block I of that file, which the file starts at BI. Now we have to read a block which is ith block. So we can directly and immediately jump to B plus I block. So with this allocation method, the direct access to the blocks is also possible. So note down, this is very important. Sequential as well as the direct access is very, very important feature of contiguous allocation. Now, there are certain problems with this. Remember in our main memory section, we were discussing about external fragmentation. Now, what is external fragmentation? Because we are allocating the contiguous block. In that scenario, we will be having external fragmentation. Now, what is external fragmentation? It is because it may be possible that even the allocation is done and we have left with the space. Now, those spaces cannot be used by other files because they are separated. So we are actually allocating contiguous space. So those small spaces which are distributed cannot be used, and that's why it is called external fragmentation. Now, this very thing is also important to note down what is external fragmentation. Now, as the files are allocated and deleted, free storage space is broken into little pieces, and that is called external fragmentation. Now, one of the strategy to prevent this is to compact all the free spaces into one contiguous space, and that solves the fragmentation problem. So we discussed about the defragmentation. The defragmentation is a process of moving the free spaces towards one end of the disk and all the use spaces to the other end of the disk. So that's why it'll help us to basically utilize the free space, and the process is called defragmentation. Another problem that contiguous allocation is determining how much space is needed for a file. So there are two possibilities because we never know what would be the size of the file. It may be possible that the file is growing. So, and we have allocated a particular file, let us suppose B blocks only, and as it is growing, it may need more space. Now, in that scenario, because we are allocating a contiguous allocation, the whole bunch of the block or the cluster or the group of the block has to be contiguous. So how to handle that is the first solution is that the user program can be terminated with an appropriate error message. Now, this is one way. The other way is to find a larger hole, which is large enough to hold that file and copy the contents of the file to the new space and release the previous space. So that is one way of handling the which is a growing file in the contiguous allocation method. Now there are other ways too. So what is done? A contiguous chunk of space is allocated initially. If it proves to be not large enough, then another chunk of contiguous space called extent is added. Now this is basically linking. There is a link to that. So there is a linking. So from one contiguous allocation to the another contiguous allocation, which is extent, there is a link which is established. So this is kind of hybridization of two methods. One is a contiguous allocation, and for adding two extents, like one contiguous allocation, and then there is another extent, which is again a contiguous allocation, a link is established. So that is the way first part of the file is here. The second part of the file is on this very location. Now, internal fragmentation can still be a problem if the extents are too large, and external fragmentation can become a problem as extents of varying sizes are allocated or deallocated. So what does it mean? That there are some solutions for handling problems, those are there, but though, and each and every solution is either impacted by internal fragmentation or external fragmentation. So no approach is again very useful, and every approach is suffering from certain problems. Now, contiguous allocation, what is happening, how to map it to the physical block? We have a logical address that is there, and from that we have a block size. Now the block size here is 512 bytes. Now this division is performed. The logical address divided by our block size, we have quotient and we have remainder. And from the quotient, we will get the Q plus the starting address and displacement into the block. So we have the block to be accessed is Q and displacement into the block is R. So that is how we will be mapping the addresses onto the blocks. So this was discussed earlier also, but here, for example, count a file that starts with from 0th block and has a length of 2. So 0 and 1, these two blocks are allocated to file count. Similarly, we can see that for file F that starts from block number 6 and the length is 2. So because it is contiguous allocation, so 5, 6 to 7, 6 and 7 are allocated to it. So we can see the other examples for larger files also. Now, the second method that is there is linked allocation that solve all the problems of contiguous allocation. So each file is linked list of blocks. Each file ends with a nil pointer and no external fragmentation happening because they are kind of scattered. Each block contains a pointer to the next block. So what is happening in each of the block, we have data, and within that data, the last particular section is a pointer to the next block. So free space management system called when a new block is needed. So whenever a new block is needed, this free space management system or allocation method is called. So it is reliability can be a problem. Now, one of the problem here is reliability, and locating a block can take many IO and a disk seat. So let me show you the diagram here. So this is the diagram for linked allocation. Now, what is available in this allocation scheme for a file system is that we will have a start block number, we will have an ending block number for a particular file heap. So when we start with 9, so the first block is 9. The last byte of 9th is pointing to 16. 16 points to 1, 1 points to 2, and 2 points to 25, which contains a nil pointer. And that is where the file is actually ending. So the problem with this particular file system is, let us suppose if 16, there due to the corruption in the data, 16 lost a track of this pointer. Now we will be able to reach from 9 to 16, but from 16 to 1, and thereafter we will not be able to track it. Although we will be able to reach out to 25th, but we will not be able to go inside. So we will never be able to retrieve those lost blocks. So that is one of the problem with linked allocation. So to create a new file, we simply create a new entry in the directory, and each directory entry has a pointer to the first block of the file. This pointer initialized to null to signify empty file. So initially it is pointing to null, and then the size is 0. A write to the file causes free space management system to find free block, and this new block is written to and is linked to the end of the file. So whatever we initialized with null, we keep on adding to that particular file. So one advantage of linked allocation is, in the previous one, we were concerned about the size of the file. If it grows very big, then how the file allocation will be handled, which is very clearly, kind of linked uh, structure is able to manage for this very linked allocation method. To read the file, we simply read the blocks by following the pointers from block to block. So there is no external fragmentation, and size of the file need not to be declared when the file is created. A file can continue to grow as long as free blocks are available, and consequently, it never necessary to compact the disk, which was the scenario in contiguous allocation. That is one of the advantage. Now we can see that here we are generating the address of the block and the displacement into the block to read the data or to store the data. Now, one of the things we will see here is that we are dividing by 508 rather than 512 in the previous example. Why that is happening? Because we are considering that the last four bytes are actually used for pointing to the next block. And that is where the problem starts. So if we say each pointer requires 4 bytes, then 0.78% of the disk is just used by pointers rather than information. So each file will require slightly more space than it would require otherwise. So for this, we have seen that there are so many pointers. So one of the solution that people came up with is to collect the blocks into multiples called clusters. So rather than having one block pointed out, just we will point a number of, we will point number of blocks together, and each block is called a cluster. So it may be possible that a cluster is of 4 blocks, and so these 4 clusters will be kind of contiguous, and then we can have pointers to point to the next particular cluster. That then the pointers will become much smaller percentage of the file space. So this is one way of handling the pointers, but still there will be a problem which is there. If the pointer lost, then we will not be able to track the file. That is in the table here. So this is one of the problem which is mentioned in this particular slide, is that if a pointer is lost or damaged, we will never be able to find out the file, and that creates a question on reliability. This is very important. So please make sure that you know what is the problem with each allocation. So we need to know, important point is we need to know each allocation method, whether we can use it for direct access or we can use it for sequential access, and then the problems with that particular allocation, and what are the remedies for that particular allocation. So that is must. Now, one thing that I have not discussed for this is that linked allocation is only used to access sequentially. Now, why that is happening is because we can see that whenever we have to read the file, we have to start from this pointer, this block, and we have to reach the pointer. And from that pointer, we have to reach the next. So if I want to read this very block, I have to go through 9, 16, first and 12. Sorry, 2. This is some data here. So I will say it is 10. So I have to reach 10 here. So why this is happening? Because each block contains the address of the next block. So we don't have a table of all the pointers which are used for that particular file. So this method is good for sequential access only. It is not good. We cannot use for uh, direct access. So mind this particular thing. It is also very important to know. We were discussing about FAT system, so file allocation system. This is initial, uh, file allocation system which was used by Windows, and they were kind of, having each file name in the file system, and then the start block of that particular file. So whatever is the start block, and each start block contains the address of the next block. So till next block. So that is how it was also indexing. Okay. Now the third allocation method is called indexed allocation method, where each file has its own index of pointers to the data. So rather than keeping index pointers to the very first part or the very first block and the end block, indexed allocation keeps track of all the blocks. So here this is basically a block which is used to point to all the blocks. So it will have addresses of all the blocks which are used for a particular file. So this is a logical view of indexed allocation. Now we can see that in this particular allocation, we just uh, have the address to the index block. And what is index block? The index block is a block that contains the addresses of all the blocks that stores the data. Now, the problem with this is that we need an exclusive block that will contain the addresses of all other blocks. So this will help us to do dynamic access of the data. That is one of the advantage is that we are able to randomly access the data without external fragmentation. And here we can see that for identifying the physical address, we divide the logical address by 512. So we are always using the full block plus one block is for the indexing table. So let us suppose our file needs 10 blocks, then plus one block will be used for the index block. And remember that it allows us to use random access. In Unix, we can have here what is happening, we can have more indexed tables. So this is called mapping. Now, rather than just having one indexed block, we can have double, indexing. So the outer index table or the block is pointing to inner index table or the blocks, and those blocks are further pointing toward the blocks used by the files. So with this, what is the advantage of this is that we can use this structure to look at a very big file in the secondary storage also. So that is one way of doing. Now, in Unix, we used a combination of approaches. What is happening? So here we can see that this is our FCB file control block. In that we have everything set up, and out of there we will have first 12 pointer will be used to point to direct block. So any file that can be represented or saved within 12 blocks, the first 12 blocks will be used for that. Now, these 12 are used to represent or access directly the data of that particular file. So if a file needs 10 blocks, then we just need one part of this to access the whole file. If this file needs more blocks, then what is happening? 12 will be used for the first part of that file, And then there is a single interact. Single interact is pointing to another index table or index block. What is this index block? This index block contains the addresses of further data blocks. Now then one of the entry is used for double interact. So what is double interact? Means this will be pointing to a block of indexes, which will further be pointing to block of other indexes. And then those will be storing the data. Okay. Now triple interact will be having 3 layers of indexing. So first layer here, second layer here, and third layer again, somewhere here, which will be indexes. And each of these will be pointing to data. So what is the meaning of this is that by combining different approaches, Unix is able to look at or point at or perform the indexing for a very small file as well as very, very large file. So that is how it is combined together with the indexed allocation method. Now, one of the advantages that we have discussed is that it allows the random access also. So best method depend upon a file access type. Contiguous great for sequential and random. Linked allocation is good for sequential but not random. And indexed is is very complex certainly, but it is also providing us very good random access. Now there we see that clustering can also improve the throughput. So some of the methods are used which creates the clustering. I will get back to this particular thing. And now is the free space management. Now we have been discussing that the blocks are needed and blocks are allocated. Now, when the blocks are needed, there might be a structure, data structure that keeps track of all free blocks. Okay. So in that scenario, operating systems usually uh, have a data structure called bit vector or bitmaps. And it is used to represent whether a block is free or not. So based on whether it is free or not, it is taken by the allocation method. Now, if we have, let us suppose n blocks, then there will be a bit vector of length n. If the value of that bit vector, each vector, let us suppose I say 1, 1, 1 here. So it means that block 0, block 1, and block 2 are free, and block 3 is occupied. So anyone, if it is 1, if this containing any entry contains 1, it means that block number is free. If it contains a 0, it means that that block number is already allocated. So from this, we can actually use to see which particular block is free. Now we will be storing this in the memory, correct? So this will also be in the memory. So there will be, this may be very, very large based on the number of blocks available on secondary storage, but each we have to split this into certain parts and we call that word. So let us suppose this bit is split into word. Now it may be possible that one word is equals to 8 bits, or it may be possible one word is equals to 16 bits. Now that depends upon the architecture, how many bits per word are representing. Now how to calculate and find which block is free, how to find the first block which is free. Okay. So for that, normally you will be given a bit stream. Eight. Let us suppose this stream is given. Now in this string, we have 16 bits. Okay. Now our job is to find the first block which is free. So in that scenario, what we'll do is number of bits per word. I say per word, number of bits are 8 bits. Okay. So I say 8 into number of zero value words. Is there any zero value word? So this is This one, I think it is, this one is one word. This is another word. So zero valued word here, none. So 8 multiplied by 0 plus the offset of first bit, which is available by CPU instruction. There are CPU instructions which will return us what is the offset for first bit. So this says the first bit is here. I say the block number 2. Okay. So let's say it is 2. Or I will make it 1 here, for example. Why 1? Because we keep it similar 0, 1, 2, 3. Okay, till n minus 1. So I say it is offset here is 1. So we get with 0 plus 1, and we get, okay, the first free block is available at index 1. Okay, now you may be surprised why I'm doing like this. So let's suppose like this. Four, 4, 8, one word, 4, 4, 8, another word. Now, if this is the status of bit word, we have to find out the first block, which is free. Now, how to find it? First of all, again, number of bits per word is 8 into number of zero valued words. So number of zero valued word, this value, this is zero valued word, correct? Because all are zero. So we say 1. 1 is zero valued word plus the offset of first 1 bit. Offset of first 1 bit is here is 3. So I say 3. So it is 11. So index 11th in this bit vector is the first block, which is free. So we can count 0, 1, 2, 7, 8, 9, 10, and 11. We can see that we have reached this very number. So that's how you will be able to find out the first block, which is free. This is very, very important. Okay. So this calculation is important. And remember that there is an instruction that we say we have available a CPU instruction that can provide us the first 1 bit index. Okay. Now, another very important question which you can see is we can find out what is the size of bitmap vector. Now, bitmap vector is a vector of zeros and ones, which represents the which block is free and which is occupied. Which block is free and which is occupied. Now, in that scenario, we have to make a calculation. So note down, this is important. So the first thing that will be given to you is the block size. What is block size? Here it is 4 KB. Now, when I say 4 KB, it is 2 raised to power 12 bytes. So you will convert that into power of 2. Then the disk size is secondary storage. So we say 1 terabyte. Now 1 terabyte is 2 raised to power 40 bytes. In example, you will see standard values. It won't be, I won't be asking you if you have 1.2 terabytes of memory or no. So it will be standard, either 500, 512, GB or 1 terabyte. So that's what would be the number for. Okay, so it's not going to be very, very fine granular. So I will be asking you, okay, if we have 1 terabyte of disk space and block size is this, what is the size of bitmap vector? Now for finding out the blocks, so for finding the vector size, we need that it is used for n blocks. Now we will find out how many blocks. So 2 raised to power 40, the size of the disk divided by the number of blocks. So we come up that with 2 raised to power 28 bits. So this many bits are needed in the bit vector. So we can represent this by dividing it 2 raised to power 8. We are asking the size of the bitmap. Okay. So if I divide this by 2 raised to power 3, it will become a byte, correct? So on, if I go on, this would particularly become 32 MB. Okay, so this will become 32 MB. This calculation further, I convert it into MBs, then we end up with 32 MB. So your question, the question you may see is either in the bit formation, like the answer option you will have in the bits format, or it may be conclusive onto MBs. Now remember that bit vector is per 1 bit per block. So this bits are converted into bytes and further into megabytes. And that is the result which is being shown here. So if it says that if we cluster 4 blocks, like rather than having one block and we have one particular bit for each block, but if we cluster 4 blocks together, then the size of that bit vector will become lower. So it will be divided by, so 32 divided by 4. So we will come up with 8 MB of the size of the bit vector will become 8 MB. So this will be the size. Now, this is an important question again. So two important questions are there. One is onto finding out which block is free. The other one is what is the size of bit vector. Okay. Another way of handling this free space is linked list approach. So in the linked list, we formation is there for free list. So all the blocks which are free, they are part of this free list or free linked list. So we have a head of that free space list. And whenever there is a particular block which gets freed, that will be added to the free list. And whenever it is taken away, will be removed from here. So that is how it is done. Now grouping again, rather than having one block only, we can have, group of blocks together, which will have a better impact onto the performance. And it may be possible that because the space is frequently contiguously used and freed up with contiguous allocation, extent, and clustering. So rather than keeping address of first free block, the count of the following blocks can also be counted. So sometimes rather than just counting what is the free first block, rather than doing that, what we do is, let us suppose here, there is a block which is free, which got freed. So rather than counting this, so we also count how many blocks are free after this. So that is called counting. So keep the address of first free block plus the number of other free blocks. Let us suppose 3, 4, and 10 or so, whatever it is. So that is another way of managing the free space. So there are different mechanisms by which these free space management is done. And the entries can also be used in balanced tree rather than a linked tree for efficient lookup, insertion, and deletion. So there are again various data structures and methods those can be used for management of the free space.